Hello students, welcome to Inside Physics. In continuation for the first session in my previous video, we have discussed about the diffraction due to a single slit, the Fraunhofer diffraction due to single slit. In that video previously, we have derived the condition for maxima and minima. The maxima, the constructive interference and the destructive interference. So when the plane wavefront from the light source is incidenting on a slit of width d, this light, when it is diffracted by the slit edges, it will be focusing on the screen at the point Q. So by this diagram, you can zoom it if you want to look it clearly. You can zoom and observe what the diagram is all about. So here, at point Q, if there is a maximum or minimum of intensity, that means the diffraction pattern always interferes while traveling from the slit to the point Q. These lens will converge all the diffracted rays to the point Q. So in this second session, we are going to derive the intensity pattern, intensity derivation, and we will obtain a condition for the intensity at point Q. Okay, so here, while the source is emitting a monochromatic radiation, the plane wave fronts from the source, where there is a lens here. This lens you can see in my previous video, which is in part 1. The lens makes the light waves into a parallel beam, that means parallel wavefront. These wavefronts will enter the slit, and the slit is divided into two parts, d by 2 and d by 2. The total width of the slit is d. From center of the slit, we will consider the distance OQ. When a light ray after diffraction is passing from O to Q, we will consider in this way: every light ray diffracted from the slit is converged to Q. So there will be all the points on this focal plane of this lens, where all the rays will be focusing on points of the focal plane of this lens. This is called L2, and there will be another lens here, which you can draw this like this, and there will be a source here. The source will emit the monochromatic radiation, and these rays, after falling on the lens, they will be coming as a parallel beam, because the source at the lens is at the focus of this lens. Okay, so this is what we discussed in the previous video. Now we consider and obtain the derivation for the intensity pattern. First of all, we must have the equation for the wave equation for the wave which is traveling from here O to Q, and we can write the initial equation as y0 is equal to a cos omega t. Okay, where a is the amplitude and omega t is the phase. Here, when the plane wavefront is passing through this slit, which is divided into n strips, so each strip is of length delta x. So the total aperture, the slit width, is divided into n equal strips. Each strip has a distance, the width of delta x. Okay, so here delta x is the width of the slit. So the path length of each slit of length delta x, if the rays are coming from the consecutive slits, they will be having a path difference of delta x sine theta. We have already seen these calculations of path difference in the previous video. So here what we do is we actually take the wave equation and we will integrate between the limits minus d by 2 to d by 2 to get the equation for the disturbance created by all the waves passing through the slits at Q. So here, what is the amplitude when all the wavelets, secondary wavelets reaching from the slit to the Q? So the resultant wavelength will be, when the plane wavefront is entering the slit, initially the amplitude is A. Okay. After passing through the slit width dx, and the disturbance created by that wave at point Q is A dx. So the amplitude at this point Q is considered as A dx. So here the phase difference. What is the phase difference? Means the phase difference can be considered as omega t plus k into x. Okay, this is the phase difference of the waves coming from 0 to Q. After coming to Q, there is a phase difference for the interfering waves. That phase difference we are calculating here. So omega t plus k means propagation constant of the waves 2 pi by lambda into, this can be considered as the distance travelled from center of the slit to Q, that means OQ. OQ can be written as x sin theta. Okay, this is the amplitude and this is the phase difference when the plane wavefront is passing through the slit, and this is the amplitude and phase difference that the waves must be having at the point Q. Okay, so if we substitute these values in this equation and we integrate the equation, so that we will get all the disturbances created by the waves at point Q. Resultant disturbance. So here I will write this as y is equal to A dx cos omega t plus k 2 pi by lambda into x sin theta. I have substituted the values what we have taken in this equation. Okay, so here I can write this as y is equal to A dx cos omega t plus 2 pi x sin theta by lambda. Okay, so if you consider this as, see, I will write again here A dx cos of omega t plus, I will write k x, where k is equal to, I considered k is equal to 2 pi sin theta by lambda. I considered k as 2 pi sin theta by lambda, so I have written in this way. So this is the wave that must be traveling from 0 to Q, and this can be the vertical displacement, that is the disturbance created at Q. So if we the small distance, if you consider the wavefront, secondary wavefront is coming from a small aperture, small slit width, we can consider this as dy is equal to A dx cos omega t plus kx. Okay, after substituting the small amplitude, so the wave is coming out of the slit width dx, even in that time we can consider the disturbance as dy is equal to A dx cos omega t plus kx. So with this equation, by integrating between the limits minus d by 2 to d by 2, we can get the total, the resultant disturbances by all the waves at Q. So what we do, we will integrate this one between the limits minus d by 2 to d by 2. Why? d by 2 to d by 2 means here the slit is divided into two parts. The width is, total width is d, and this is d by 2 and this is d by 2. So if you consider this as origin, this is positive d by 2, this is negative d by 2, minus d by t to d by 2. So in these limits we will integrate. So this will become again minus d by 2 to d by 2. Okay, here a dx cos omega t. So what I will do is this cos a plus b, this is in the form of cos a plus b. We can write cos of a plus b as cos a cos b minus sin a sin b. This we know from the properties of trigonometry. See, cos of a plus b is equal to cos a cos b minus sin a sin b. This is in the form of cos of a plus b. So I can write this as cos omega t cos a cos b cos kx minus sin a, that means sin omega t minus sin b, that means sin kx. Okay, so from this I obtained this one. So we will further go with this equation as we will write this k here for further proceedings. K is equal to 2 pi sin theta by lambda. So from this I am writing here, this is y is equal to integration of dy between the limits will become the y, and this will become minus d by 2 to d by 2. Here see, cos omega t cos kx into dx minus, okay, I can write the integration is divided into two parts, d by 2 to minus d by 2 to d by 2. So here sin omega t into sin kx of dx. Okay, so from this I have taken this step and we will further proceed for the integration. Okay, so here you observe we can integrate this term and we can integrate this term where the variable is in the x. So here the integration part can be further taken as a into, see, cos omega t, we can take it out on this side, minus d by 2 to d by 2 cos kx dx. Okay, so again here if you take it this sin omega t outside, okay, so you can have the a here also. So after multiplying a both sides we will get a here. Here a sin omega t and the integration between the limits d by 2 to d by 2. So here sin kx dx. Okay. So here we are moving to further steps. So by integrating cos omega t, so this cos kx dx will become sin kx by k. After integrating, we will consider the formula and we will put this one in between the limits minus d by 2 to d by 2. again here a sine omega t between the limits minus d by 2 to d by 2 sin kx dx. This can be written as, we will remove the integration. Why? Because after integration this term may become minus kx cos kx by k between the limits minus d by 2 to d by 2. So sin kx will become minus cos kx by k. Okay. So here if you substitute these limits in the place of x, okay, so you can have this as a cos omega t. So okay, we will take this step in the above area. So from this what I am writing is a cos omega t. I will substitute these limits, then it will become sin k d by 2, okay, d by 2 by k plus, so minus, actually this has minus, so if I put this limit as minus, minus minus becomes plus, so I can write it as kd by 2 by k. Okay, so what about this term? This term, see, this particular term will become 0. Why? Because see, if you observe this one, this will become, see, I am writing here, this term, particular term will become, if you write like this, minus k d by 2 by k plus minus cos k d by 2 by k. Okay, so this minus we can remove, so minus minus will become plus. Okay, if you observe this one, these two terms will be getting cancelled, so this will become 0. Here see, minus k d by 2, here we have minus, minus of this one, so minus of minus will become this, we can remove this one, or you can put minus here and you can have minus here, or you can put plus here and you can have this minus removed here. So in this way we can observe this term will become, this may become equal to 0. Okay, so this term will become 0, so that this whole term we can remove. So what is the remaining term? This will become 0. This whole term will become 0. So we'll move to next step. So here what we can write, a cos omega t, see, 2 sin k d by 2 by k minus 0. So we can have this term 2 sin k d by 2 by k. Okay, we'll take this 2 outside. So this can be written as 2a cos omega t. Okay, so we'll put here, in place of k we can put 2 pi sin theta by lambda. If you put that one in place of k, if you put that one, what happens? See, k 2 pi sin theta d by lambda, okay, into 2, there is 2 here, and by k 2 pi sin theta by lambda. Okay, so here these two will be getting cancelled, so these two will be getting cancelled, right? these two and these two are cancelled, and this one and this one is also got cancelled. So what happens here? A cos omega t. Okay, so here can write pi d sin theta by lambda sin of pi d sin theta by lambda by pi sin theta by lambda. Okay, here see, if I take d here, multiplying the numerator and denominator by d, what happens? I can write from here, I am writing here, you observe this one, a cos omega t. I am multiplying this numerator and denominator by small d. So this equation will become AD cos omega t. So sin of pi d sin theta by lambda by pi d sin theta by lambda. Okay, so here we are coming to the end of this derivation. Here if you observe, this is y and this, see, a d cos omega t, and we can rearrange the terms and we can write it as sin of pi d sin theta by lambda by pi d sin theta by lambda. Okay, so if you observe these terms, we can rearrange them and we can have this as cos omega t. Okay, so here see, I will write this as y is equal to a theta cos omega t, where this whole term is considered as a theta. The amplitude obtained by the diffracted rays by passing through the slit of width dx, and they are diffracted at an angle theta. So all the interference pattern will depend on the diffracting angle only. Okay, where a theta is equal to AD into this part. This whole part is considered as a theta. So if I say this pi d sin theta by lambda, I consider pi d sin theta by lambda is equal to alpha. Okay, so this whole term will become, this term may look like pi d sin theta by lambda will become alpha, then this can be written as AD into sin alpha by alpha into cos omega t, where here a theta can be represented by AD sin alpha by alpha. We can write here a theta amplitude is equal to a naught. Okay, a naught, and this is a naught cos sin alpha by alpha. Okay, a theta is equal to a naught into sin alpha by alpha and cos omega t. Okay, so this is what the amplitude, and this can be written as, if you consider this as a theta is equal to a naught into sine alpha by alpha. So by this we can write the intensity. We know that the intensity of the light wave is always proportional to square of the amplitude, right? Square of the amplitude. So in this term, in this way, we can write it as the intensity I. The term intensity I can be written as I theta. You may have this equation represented in intensity form. I theta is equal to I naught into sine alpha by alpha whole square. Okay. So if you observe this one, this equation, the intensity pattern by the diffracted rays, where they may be interfering destructively or constructively, the intensity is dependent on the alpha. So where alpha is equal to pi d sine theta by lambda. Okay. So you may have this I or I theta. I is equal to I naught. Why I have written square means the intensity of the light is always proportional to square of the amplitude of the wave. So here where we can say alpha is equal to pi d sine theta by lambda. So the diffracting angle plays a key role here for the intensity of the wave. So depending on the diffracting angle, so thereby the alpha value will indicate the intensity pattern, and the intensity is dependent here directly on the angle of diffraction and indirectly on the value of alpha. So how the intensity pattern look like for a Fraunhofer diffraction in single slit? So we can have that understanding by drawing a diagram. By considering this one, we can also write this term as sine square alpha by alpha square alpha. We can write in this way: I is equal to I naught sine square alpha by alpha square. Okay, we'll observe the intensity pattern by drawing a graph between diffracting angle and the intensity. You consider the center. Here there is a central maximum. Okay, so to go from central, there is a origin here, and this is origin. We can have these values as pi, 2 pi, 3 pi, like that. Okay, on the one side it is pi, 2 pi, 3 pi, the positive side. On the left side you may have the values as negative. Okay, so here there will be the intensity is taken on y-axis, and this angle of diffraction and is taken on the x-axis. So for this, what we observe is the intensity pattern will look like, see, there is a central maximum with highest intensity, and the intensity will be going down like this, and it may fall down. This is the first order, this is for second order, and we also have this as first order and the second order. The second order may not be so intense, it may not be so clearly visible, so but the central maximum I is very, very visible because it will have the highest intensity. Okay, so in this way we can analyze the intensity pattern obtained by the single slit after diffraction. You observe the intensity in terms of a bright or dark band. This is a bright band and this is always accompanied aside by a dark band, and again there will be a bright band. So dark is always represented by some black color. Okay, so the central maximum, first order bright fringe, first order bright fringe, after that this is a first order dark spot, this is the first order dark spot, after that it will follow like that, second order bright and second order bright on the right side. So in this way the central bright spot will be having the maximum width and maximum intensity. So by you go towards the left and right sides, the intensity, if you look this first order intensity, it is somewhat far lesser than the central maximum, and the second order intensity has further fallen from the first order intensity. So it is not so visible and the intensity is very less. Okay, this is the pattern of single slit. This is diffraction, which is called Fraunhofer diffraction. And if you compare these intensities with the central maximum, the first order intensity may be 1 by 22 times of that of central maximum, and if you compare the second order intensity, it will be 1 by 61 times of the central maximum intensity, central bright spot. So in this way we analyze the intensity pattern also with the help of this graph, and we already have this formula to obtain the relation between angle of diffraction and the intensity. So this is all about in this session, and we will move to further sessions to discuss some more topics on diffraction.